So, good afternoon and welcome back, everyone. I am Sharon, your host for the session. For those who you are joining just now for the session, the recordings of the previous session are available on Discord as well as Hype. So do check it out. Just before getting started, I'd like to remind you that you will have the chance to raise questions during the presentation to the speaker. You have to just put it in the chat box. We'll be addressing them at the end of the session in the Q&A session. So now I'd like to introduce our speaker, Jayesh Parashar sir. Jayesh Parashar sir has worked around the globe for various clients in the financial services sector and has an experience of more than 24 years. He is a physics teacher by passion and has been associated with quantum computing for years. He is also an IBM Quizzkit advocate who loves to learn, share, discuss new concepts of quantum computing. So without any further delay, I'd like to hand it over to you, sir. So please take over.
Oh, probably my second monitor is connected, so let me just take it off. So now, hopefully, my screen is visible and full screen mode.
Yeah, it's fine, Jayesh. You can start.
Okay, thank you. So, as my name is Jayesh Parashar, and I thank you again for the kind introduction. In today's session, we are basically going to, uh, talk about two things. One is the quantum mechanics. I'm gonna give a brief introduction to quantum mechanics. We'll see how the different rules in quantum mechanics have evolved over the time, especially in last 1 century, and then how it is important in the quantum computing that you are studying in this fall fest event. And then the other thing that I'm going to cover in the next half or the second half of this session is uncertainty principle. So the uncertainty principle probably everyone is aware of, delta x delta p thing, but it is more than that. It is something that has a very deep meaning. So we'll see, like, how we can in fact even implement it in Qiskit and play around it and see like how nature works. So here is the agenda, and I'm just trying to enable a pointer so I can point you at the right position. So hopefully you are able to see. Okay, I think it looks good. So we let me go through the agenda quickly. We are just going to look at a basic definition of computer and computation. Then I'm gonna cover like the differences between classical and quantum physics based on the objects they describe best. Then I will cover a brief history of quantum mechanics and couple of slides, and then I will look at the key concepts of quantum mechanics, those we use in quantum computing, and then we'll jump to understanding more about the probability and chances. uh, then I'll present you an imaginary exotic coin. With the help of that coin, we'll try to understand the uncertainty principle. uh, then at the end, I'll give you a clue on how you could implement or see Heisenberg uncertainty principle in the Qiskit. How you see it in action in the Qiskit, and then we'll conclude the session with question and answers. So coming to the very first slide, a computer as we define, whether it's a like quantum computer or classical computer or computer based on some other set of rules, a good computer should be able to transform information. And one thing we have to remember is information is physical. So I'll come back to that. But a good computer should be able to store and process information, and it should be able to do so in a definite time. It should not take days or years to compute something. And the other property for a good computer to have is the universality. So we should be able to port any problem and present any problem in such a way that like computer could understand it. So our input should be in such a way that we can port any problem to uh, as an input to that computer, and it should be able to calculate output accordingly. Now computation is a broader term. It is not only like arithmetic calculation, it's not only like doing plus minus division, but it is more than that now, because the definition of computer or computation is also broad. Like, when we talk about artificial intelligence or deep learning, uh, we can see an equivalence between our human brain and then computers. So computation again has evolved over time. This the definition of computers now, it include logical reasoning, artificial intelligence, or even thought process. Now, coming to the types of computers, we have two types of computers. One is analog, that works with continuous values. Another one is digital, that works with discrete values, and you will see like how it makes a difference. Now, understanding the physics behind the computer. So the computers that we work with, they work on the Newtonian physics or the classical physics. But what it is, so based on the objects, physicists have divided mainly like all the objects in three parts. And these three parts could be best understood with three types of physics, like three, not type of physics, but three rules, or set of rules defined in physics. So this set of rules are called relativistic mechanics, quantum mechanics, and classical mechanics. So the very large object, like the moon, sun, nebulas, galaxies, the behavior of such object could be best understood with the relativity, both like special relativity and general relativity. In special relativity, we mostly talk about like speed, when it is in comparison with the speed of light. But relativistic mechanics involves both. Now, the object which are of the medium size, like that we deal with every day, your computer, humans, buildings, insects, grains, etc. So the behavior of such objects could be best understood with the classical mechanics, and we also call it the Newtonian mechanics, or Newton's laws of motion, Newton's equations. uh, what it does, it allows you to calculate, like if you were given a force, and what is the initial position of an object, like, and if a force is applied to it, you are able to calculate what would be the where that object would be after few seconds or few minutes or so. But object of very small size and small mass, like atom, electrons, neutrons, any subatomic particle, quarks, etc., or energy, in fact, because mass and energy are equivalent in physics. So when we are talking about like something of a small size, by that I mean like both mass and energy. So when we talk about energy, we are talking about photons. So behavior of such objects is best understood with the theory that has been like evolved over a century. And there were multiple like principles have been developed, so it has become a framework. So this set of rules, or this framework, we know it as a quantum mechanics. And this is the best way we have come up with, like to describe the behavior of the subatomic or atomic particles. Now, there are two important difference between classical and quantum mechanics. So the first thing is in the word itself. Like when we say quantum mechanics, so how it has started. So it has started on a very basic principle, very simple to understand, that quantum mechanics, it does not mean small, it means something indivisible. So what initially thought was that everything is continuous. So what it mean by continuous is the values between 0 and 1. So you can have 0, zero point 0.9, zero point 0.8, and then between zero point 0.9 and zero point 0.8 you could have 0.85, 0.86, and so on. So those are like continuous. But when you say you could either have 0 or 1, so that is discrete. Like that is something we call comes in packet. It's kind of if you talk about energy, the energy is quantized, or the charge is quantized, or the angular momentum is quantized. It could be like either up or down. So this is what the basic building block of entire quantum mechanics, that things or the properties that we measure, that comes in chunks. So either you have that much or you have nothing. So there is no in between. So this is one difference between, like, the theory of Newtonian mechanics or the classical mechanics and quantum mechanics. Another important difference is how we measure things. So in quantum mechanics, we talk about probabilities. So I'll give you an example. Let's say, like, if you have a car moving in a direction with 10 meter per second. So after 4 seconds, you could say, like, the car will be at 40 meters from the origin. But in case of an electron moving with the same 10 meter per second speed, and after 4 seconds, the way you will ask your question is, what is the probability of finding that car at a location 40 meter away from origin? So you are asking about probability, means there is a intrinsic, like, uh, randomness, or I would say, like, uncertainty. So that's, sorry, not randomness, but the uncertainty is the better word. There's an intrinsic uncertainty about the value of a property itself. So what you look for is, you look for probability, and we'll try to understand it more in next few slides. So coming to the quantum mechanics, in 19th century, there was a good understanding developed upon how electromagnetism work, and the theory or the equation, you probably have heard about the Maxwell's equation. So Maxwell defined the electromagnetic waves, and he said, like, the electromagnetic waves are different than mechanical waves. I mean, it is, of course, it is a wave, but it is, instead of the medium, the particles of medium going up and down or vibrating, it is the electric and magnetic fields which are going up and down, which are oscillating perpendicular to each other. And when this fields oscillates on a particular speed, when they gain a speed, they keep on creating both magnetic and electric field perpendicular to each other, and this is how a electromagnetic wave is formed and it travels. So about, when we are talking about waves, there are two properties of waves. One is, like, it's wavelength. So the wavelength of a wave is equal to the distance between two peaks, and other one is frequency. So frequency is how many wavelengths are passing, uh, passing from a point in a unit time. So if your wavelength is larger, if your wavelength is covering large distance, then you will have less waves, like less wavelengths passing through a point in a given time, in a unit time. So the frequency will be lower when wavelength is larger, and frequency will become higher if your wavelength is small. And that what we see when we see the visible light, the spectrum of electromagnetic waves. We see an ultraviolet region here, if you can note. So this is higher frequency region than visible light, and then we have the infrared frequency region, that is the light with larger wavelengths. And then if we further go, we can see radio waves, which are, like, even with the larger wavelength. So more waves are contained in a specific period of space, and in a specific space, the more strong or more powerful the wave would be. So as we have seen, like, we are always wants to away from X-ray radiation or UV radiation, because it contains, like, it has a lot of frequency and it contains a lot of energy. Now what happened at the end of 19th century, and this is how the this concept of quantization came in picture, is there uh, was an experiment performed with the black body. And a black body is something that emits radiation. It has some temperature, and based on the temperature it emits radiation. So when you heat up a material, then the amount of radiation that comes out of that material only depends on its temperature. And it was noted that when the experimental data was collected and then the classical predictions were made, this is the classical prediction. What it says that when you increase the temperature, you are going to get infinite amount of radiation out of that black body. But the data that you see in red, green, and blue color, the data points on this graph, it shows that when you even in fact, like you heat up an particular material of the black body, the ultraviolet radiation that comes out of that black body, it goes down suddenly. So there are all type of radiation you get, but ultraviolet radiation is very less, and maximum at around 5000 Kelvin you maximum get the light in the visible spectrum. So the classical theory predicted infinite radiation. The observation suggests that there is a sudden drop in the when you move to the ultraviolet range. And Max Planck, he suggested that maybe there is like some adjustment we have to make, and he introduced a constant called the Planck constant, and he adjusted equations such that energy is not continuous, but it comes in chunks. Like, so there is a like bundle of energy, and the energy cannot go lower. When he made that change, everything works fine, his equation and the experimental results matched. So this is how you could say it is a birth of quantum mechanics, or the birth of quantization. Then in 1905, Albert Einstein explained in the photoelectric effect the same thing. He said like not only the radiation from black body that is originated from the atomic vibration, but also the light that is also quantized. The light also comes in packets, and he called it light particle. So it was like very much well established by that time that light is wave, but Einstein suggested that maybe it is not wave fully, but it is also particle. It's like the light coming as a packet, as a bundle. So that created some confusion and debates around the scientific community that time. Then in 1920, Bohr suggested that not only the atomic vibration energy or the light energy that comes in bundles, but the electrons also follow the same quantization, and they revolve around the nucleus in predetermined orbits. So these orbits can't be any value. Like, these orbits are some predefined energy values, and when electron jump out of one orbit and moves to another orbit, we get a photon equal to the difference of energy. So uh, everything like that was discussed at time was like whether light is a wave, or then another experiment was performed, and I put a link of same. It's a Dr. Quantum video, very good video. I mean, everyone should, if you would like to learn, you should watch that video multiple times. It talks about an electron passing through double slit, and when an electron is a particle, but when it goes through double slit, it behaves like waves. So it shows interference pattern that is not possible with the particle. So this type of experiments actually creates a lot of questions, and that is where, like, the scientific community there, that is where like we get an opportunity to explore things that explore something new, explore things that can describe that behavior. So Louis de Broglie in 1924, he postulated something. He said, maybe everything is a particle as well as a wave, but when things are very small, then the wave nature of that particular thing is more visible. He has given a formula that says lambda equal to h divided by p. Here lambda is the wavelength and p is the momentum. So more the momentum is, lesser the wavelength is, and vice versa. But what he said, like, with the small particles, their wavelength is significant. So when the wavelength is significant, the wave behavior of that object or that particle is more visible. But when we talk about our day-to-day objects that we interact with, maybe a tennis ball, the wavelength of that ball comes at around 10 to the power minus 35 meters. So that is very small, and with smaller wavelengths we see negligible wave effect. So this was an important point, that the wave particle duality. So moving next, there are some more important uh, observations and principles. Those were discovered, and one of them was Stern Garlic experiment that showed that the spin of electron is quantized. It can take only two values, either up or down, that we normally denotes with +1 and -1. And when you look into the quantum computing, the very basic uh, building block of quantum computing, or the quantum information qubit, when you look at it on the block sphere, then you see like the plus and minus on z-axis, x-axis, and y-axis. So you can easily correspond it to what Stern Garlic experiment showed us. So either when you take measurement along z-axis, either you get a +1 or -1, either you get a state 0 or you get a state 1. Similarly, with the when you perform measurement along other axis. So moving next in 1926, Schrodinger invented the wave function, and on the same year later, Max Born proposed that uh, what we see in Schrodinger's equation is a probability wave, and Schrodinger equation has its own place in quantum mechanics. It's like Newton's law of motion, like F equal to ma, where we put a force on an object, we can predict its behavior. And here we cannot predict the exact behavior, but Schrodinger equation allows you to calculate the probabilities. So given the current state of a quantum system, you should be able to calculate the probabilities, if you use Schrodinger equation. And there are multiple forms of it: time dependent, time independent. However, in quantum computing, Schrodinger equation is used a lot, maybe hidden, like when you even try to reset a qubit or initialize it. This is what we used in quantum computing. We use the Schrodinger equation, and also in many algorithms, the Schrodinger equation is used. So it is a good thing to remember, and maybe explore it a little on internet. You will find many articles. So next one is our major topic that we are going to discuss, the Heisenberg's uncertainty principle. So it was explained mostly with an example that if you would like to know the complete description of an electron, and by complete description I mean the position and momentum for time being, let's say that is the complete description, then you cannot get that complete description, because if you measure the position you will have more uncertainty around the momentum, and if you measure momentum, then you have more uncertainty around the position. The way it is explained is like, in order to find the location or the position of electron, you have to hit it with an photon, then only you can precisely calculate. But this example creates more confusion, because people may ask, like, why should I get a measurement on position using a photon? Maybe there is another way I can get that position. So maybe let's discover it more. Let's come up with some creativity and see if we can explain it better. But the basic thing that it says is, it is impossible to get the complete description of a quantum object, or a quantum system. So in 1982, coming to quantum computing from quantum mechanics. So in 1982, there was a conference held between many physicists, along with Dr. Richard Feynman, experts from MIT and IBM. And at the end of the conference, Dr. Feynman, he suggested that we are trying to simulate nature with classical computing, and that is insufficient, because nature itself does not operate on classical rules. It operates on the rules of, it follows the rules of quantum mechanics, as long as we understand. So why don't we build a device based on the principle of quantum mechanics, and there we can probably do some manipulation using our engineering techniques, and maybe we would be able to simulate nature better with quantum mechanics. So this is how it started. Just wanted to check on my pace. Is it my are you able to understand me, Dr. Gandhi? Is the pace okay, or shall I reduce it?
Yeah, Jayesh, it's okay. We are
Okay,
able to follow you. Yeah, fine.
thank you very much. So, moving to next slide, the key concepts used in quantum computation. So there are three, important concepts that we use in quantum computation. Three important quantum mechanics concepts that we use in quantum computations, and these are superposition, interference, and entanglement. So, what does it mean by superposition? Superposition means like when a quantum mechanical object, or as I said in the first slide, the information is physical, right? So if we are talking about classical information, we talk about 0 and 1. We talk about the voltage, whether the 5 volt or 0 volt. Similarly, in quantum computation, we have to have some device, maybe the spin of electrons, whether the spin is up or down. And what happens with the quantum object, they have a property that they could remain in multiple states at once. So we say like the electron is spinning, I mean not spinning, but it has an spin up and down. So if an electron passes through a magnetic field, then we can observe that it is either going up or down. But as long as it is not uh, going through, or we are not measuring its spin, we are not measuring whether it will go up or down, it remains in both up state and down state. And this has been verified in experiments, and you would know more about those experiments. You could in fact do those experiments using Qiskit from the ease of your home, and from your laptop. So the superposition, it says like the quantum objects can remain and represent multiple states simultaneously. And mathematically, you can derive that when you write the equation of a qubit. You write psi equal to some complex number multiplied by 0 plus another complex number multiplied by state 1. So what you are saying is like that qubit is in both state 0 and state 1. So there is an probability amplitude associated with state 0. There is probability amplitude associated with state 1. It is important to remember and not get confused with two objects. We are talking about one object in two state. We are not talking about two objects, each one is in different state. So those we call mixed configuration, but we are talking about superposition. Superposition is different from a mixed state. So there's another term that is associated with superposition, and it is called the collapse of wave function, or the collapse of the wave nature. And the superposition is due to the wave nature of the quantum object, because as the waves, they can like superimposed on each other. But when we look at if we talk about the dual slit experiment with electron, and when we are not sure what path an electron is taking, whether the electron is going through the first slit or the second slit, it remains in superposition, and it shows us an interference pattern at the back of the screen. But if we put a detector device on one of the slit, and then we do not see any interference. What we see is like only two bars, and it is because of the collapse of wave function. So collapse of wave function says that if you make a measurement of a quantum object, it will uh, take one of the possible values. So in qubit there are only two possible values, spin up or spin down, or 0 or 1. So if you are not looking at it, it is in both 0 and 1. When you look at it, it will either become a 0 in state 0, or in state 1 it will either become a spin up or spin down. So I would also like to mention about the many world interpretation, that does not believe in the collapse of wave function, but the way it describes the behavior, that on taking measurement you either get 0 or 1 or up or down. It says like if you take the measurement of an electron going through a magnetic field, or if you perform a measurement on a qubit, if you see a 0, then there is a like one happening in another universe. So it like like the science fiction movies, it talks about the concept of multiverse, and it is mathematically, it has been proven that it may be possible. So why I talked about it is like, if we look at many world interpretation, it is easy to understand the functioning of quantum computers. So in quantum computers we can have parallel computations at the same time, and these parallel computations are happening in multiverse, in the different universes, each taking like one logical path, or it taking maybe same logical path with different input values. So we can perform the same computation on different set of values. However, the superposition does not give you like any advantage, because things are happening in multiverse. You do not have a control on another universe. So what we do, sorry about that. So sorry about that. So in with just only many world interpretation, we cannot get any benefit. So let's talk about the interference. That is the second important quantum mechanical concept used in quantum computation. And what interference tells us is like, when you have waves superimposed on each other, and if the crest or the peak of one wave falls on the peak of another wave, then you get an increase in amplitude. And if things happens otherwise, if the peak of one wave falls on the crest of another wave, then you get destructive interference. So in quantum computation, we have phases associated with each state. So as I said, like particles behaves like waves. So similarly, we can think of a system in different states is like different waves. So if a system could remain in state 0 and 1, there are waves associated with a level 0 and level 1. And if we have two waves associated with level 0, we can see if those two waves are in phase. If those are in phase, then we are going to see a boost in the probability of getting state 0. If we in case of state 1, if we have like two waves associated with state 1, but those are like with opposite phase, then state 1 is going to be cancelled. And you can do that. You can see that by simply putting like 2 3 gates in cascade. You can put an header mod, then you can actually put a phase gate in between, and then you can put another header mod there and play around that, like adjust the phase. And then you see like how the zero state is getting strength, or how one state is losing probability amplitude. So those are like good exercises to do, and it will give you a better understanding of both superposition and interference. So one thing to keep in mind is like, without interference or the phase in quantum computing, uh, there is no advantage of it. Like you if you cannot interfere uh, the waves associated with different states. You cannot take any advantage of parallel computing that is happening in multiverse. uh, the next point is entanglement, and entanglement could be described with lot of there are a lot of definitions of entanglement, but the best way I found is to define it as a correlation between multiple quantum objects. So let's say if you have two quantum objects and those are entangled, those are correlated in such a manner that when you perform observation on one quantum object, you come to know about the uh, same property or the same information associated with the second object. So you take measurement, you have A and B entangled. You take measurement on A and you measure its spin and along the x-axis. You come to know the spin along x-axis for another particle, another quantum system or electron that is named as B. So entanglement has like several application. You know, it's it is most used in at this moment. It is being used in quantum key distribution. It's like a security protocol. So what we do, like we generate entangled particle, we send it one to Bob and one to Alice, and then we try to come up with a secure key. And principally no one should be able to look at those keys due to uncertainty principle. So things in quantum computing are not hype. As you might have seen like some videos, there are some real ongoing real world applications. The governments around the globes are investing a lot. China, India, Russia, Australia, US, they are investing a lot in quantum computing just because of the quantum key distribution, or just because it could give you a you know a protocol that no one can break, right? So it is a protocol that is protected by the laws of nature. So this is just, and this is quantum key distribution is just a very simple and practical example. So when you see a video about the hype on quantum computing, don't just believe on it. Check things by yourself. So coming back to entanglement, entanglement is not only used in secure key distribution, but it is also used in almost every quantum algorithm. What you do, like you prepare two sets of qubits, and you entangle those two sets or registers, and you take a measurement on one register, and when you take the measurement on one register, you come to know what are the possible outcomes on other set of registers. So in short, quantum algorithms are designed to execute all possible computational path, and it cancels out the undesirable. Yeah, sorry about that. So it cancels out the undesired paths, and it boosts the probability of getting the right or desired outcome. And let me just put it once again. Yeah. So is it visible? Sorry, I was just trying to move a box.
It's
Is
visible,
it?
Jay.
Oh, okay, thank you.
Yeah.
So coming to evolution of quantum computing, as I mentioned before, it was conceptualized around 1980, and then there were progress made on same in 1994. Peter showed he showed that it is possible to break the RSA encryption using quantum computation, and then that gathered a lot of attention and money required for research. In year 2000, there was a company was formed named D-Wave. It is the first company who actually sold the very first quantum computing machine uh, to someone in US. I forgot the name. As an company that deals with the fighter aircraft. So there was a lot of money started flowing in from after year 1994, and then DOA was formed in year 2000, and then in 2016, as IBM was already working on this technology from 1982, in 2016 IBM actually put the real quantum computer on cloud. So the major development and interest and like community building started after 2016. And now just 5 years after, and you probably have heard Brian, I'm not sure if there was a session from Brian, but he mentioned that now we have millions of users, like those are using, those are trying to build community, find algorithm across the globe. So that is a big development. So we are going to look at uncertainty principle and our remaining part of this session. So shall I just stop for the questions, or like we are going to deal with questions at the end?
We'll have question answers at the end, Jayesh.
Okay, thank you. So I'll move ahead with the session. So before we uh, take a look at uncertainty principle, like what it is and how it works, I'd like to revisit couple of terms like the probability and randomness. So for same, like I'll take a real life example. Maybe when we make a plan, let's say a real time example that we created. Let's say you woke up one day and you created a plan to go for picnic, and it's a very bright sunny day, and it is a pleasant day. um, you have made a detailed plan that, like, you will visit and so restaurant, you will pick food there, or you are going to visit that particular sightseeing location, and then you are going to take that route and do so and so. What are the chances that, like, you are going to fulfill that plan? So you could say like maybe 99% based on the experience, because if a day start pleasant, there are like very much chances that like it will remain pleasant. So and you should be able to perform what you are doing. But maybe there could be an engine problem in your car, or maybe there uh, is some emergency from office or family that may disrupt your plan. So the way you can think of it, mathematically, you could say like, maybe 99% chances are there that like I'll be able to fulfill my plan, and there's a 1% chance of failure. So let's mark it as like, the things will happen as you planned as success, and things will not go as you planned as failure. So in our picnic example, the chances of success is 99 out of 100, and chances of failure is 1 out of 100. So what does it mean by like, 99 out of 100? It tells us like, or the 99%, what does it mean? It says like, if we repeat the same plan or the same experiment 100 times, then 99 uh, times we are going to be okay, like, we will get a success, and one time there may be some emergency or some other reason, because of that we won't be able to fulfill our plan. But if we think further, if we think deep, is like, repeating that particular experiment 100 times will give you an exact result. Is like every time you repeat 100 times, you will get 99 times you get success and one time you get failure. It is not like that, right? I mean, sometimes you might have to repeat it like 1,000 times or 10,000 times to see the pattern, like to see the chances, to get the chances. And chances are nothing but it is like the measure of probability, right? So if you repeat an experiment, let's say 1,000 times, and it may happen that all 1,000 times you get success. But if you repeat it like 10,000 times, then only you would be able to get the failure and success both. So how many times you will have to really repeat an experiment to get a good idea of or to get a probability of success and failure? So it turns out that like you might have to repeat an experiment infinite number of times, but in practical world you could just like repeat a plan or experiment very large number of times, and the number of times you have to repeat depends on how far your probabilistic results are. So if in simple words, if like you are tossing a coin and the results are like 50% head and 50% tail, then it might be just sufficient to toss that coin for 10 times, right? Now I mean, out of 10 times you may get 4 or 6, and if you do it like 50 times, that is enough. But let's say like there is a chance of failure is 0.001 uh, percent, right? So in that case, you will have to do more repetition to get the exact probability, and this is what is encoded in nature, right? That you know even the distant possibilities could happen, may realize there is a chance. Maybe that chance is very minute. Like in our example, there may be a chance that like a comet fall from sky and that will disrupt your plan. So that chance is very minute, but still there is a chance, right? And that is what happens when we talk about an individual experiment, when we do not consider like the group of experiment, but when we talk about an single isolated experiment, then anything could happen. And this anything is basically the element of surprise that we cannot avoid. This is inbuilt in nature, and this is what become more visible when we study smaller and smaller particles. When we study smaller particles, like this uncertainty become more and more visible. So the way like the outcome of an individual experiment remain random, uh, it gives a framework of uncertainty, and that is what we try to explore more with an thought experiment. Excuse me. So we will do a thought experiment in which we will take a coin, and we will call it an like exotic coin. That's a special coin, and we will try to get its complete description. So this coin has two properties. The first property it has is its color, and the second property it has is temperature, right? So we devise two type of measurement to get it color and temperature. And remember, we this is a coin, exotic coin, that we are not going to toss, but we are taking it in place of electron, because I found it more intuitive or more explainable if I take a coin instead of electron and I go after its position and momentum. So, like electrons' position and momentum, this coin has two properties: the color and temperature. For color, it can have two values. Either it could be red or green, and for temperature, it could have two colors. Two temperature, two values: the warm and cold. So, color could be red or green, and temperature could be warm or cold. So, since it's a exotic coin, we cannot look at it and feel it at the same time. So we have to define two measurements. The first measurement we defined is MC, to measure color, and it is for this measurement we will simply rely on our eyes, and we look at it, we see whether it is a red or green. For other measurement, we will use our touch sense. So we are going to touch. We cannot look and touch at the same time because these are two different measurements. These properties are mutually exclusive, in terms of physics. So we touch that and we feel whether it is warm or cold. So let's try to get the accurate value for both of these properties. And if we are able to get accurate values of both these properties, it means like we have got the complete description. So initially we looked at the coin at look red, so we have noted down that the color of our coin is red. Then we use another setup, and this time we touch the coin, so we found it warm. So we have written our observation here, like the color is red and the temperature is warm right here. And we just wanted to make sure that whatever we have recorded still stands, right? So what we did is we noted, we would like to observe the temperature again. So we have again like touched the coin and we found it warm. So we are like now confident that okay, temperature is warm, the value of temperature is warm, the value of color is red. But what happens, like, we wanted to be double sure that like the color is really red. And when we looked at the coin, when we used the MC experiment again, then we can find that particular coin as red or green with equal probabilities. So every time we take a measurement of temperature, we reset the color, and every time we, you know, take the measurement of color, we reset the temperature. And you can actually, if you will go through this table, you would be able to understand it better that uh, taking the measurement of one aspect disturbs the other. It is like a square balloon, and the width and the height of the balloon is the measure of the uncertainty. So if you can reduce the uncertainty on the properties associated with horizontal axis, then balloon is going to expand vertically. So you will be more uncertain. Like in case here, if we measure the temperature, we'll be uncertain about what the color would be, and if we measure the color, we'll be uncertain about what the temperature would be. So this analogy of this coin, we can correlate it with the electrons position and momentum, or electrons spin in a particular axis, like either the x-axis or z or x or y. More we have idea about, like if we take a measurement on of the spin along the x-axis, then we will have no idea what would be the spin along the z-axis. So in the next slide, actually, I showed it on the block sphere. And basically what you see here, if my pointer is visible, that with each spin, like along the z or x or y axis, there is a value that is like +1 and -1. So +1 we call is associated with state 0, or state plus, or state plus I. And this 3 axis, as you could see, like, if I'll measure the spin along z axis, and if the electron is going like that, there's a magnet here in the z orientation, and then electron, let's say it has moved upward, so it says like its spin is +1 and it is in state 0 as far as our quantum information is concerned. Then if we look at this block sphere representation, we find that, like, now we have no idea of electron, what's the electron spin along the y-axis and what the electron spin along z-axis. So the z-axis is coming out of a screen. So similar thing happen, like, if you make a measurement along x-axis, or if you make a measurement along y-axis, then you will find that you lose all the information about the electron's spin across other perpendicular axis. So maybe it is like too much for for the session, but I mean, you can give it a try. What I wanted to communicate is like this kind of stuff that Dr. Richard Feynman once thought that we will be able to perform the experiments on our computers. It's like doing a real lab experiment. So you can do this kind of experiment using IBM Cascade software, the Cascade SDK. And what you could do, like, you can take a measurement along z-axis, and then just by putting an Hadamard gate, you can change that measurement to taking measurement along x-axis. So maybe you can give it a try, and if required, I'll put an example of same and discard. So I probably, yeah. So I'll just conclude this session with couple of observations that we have gathered from this experiment. Is like, the first observation is, when we worked with this exotic coin, or if we work with electrons, spin or position and momentum, one thing is very clear, that we are prohibited from getting the complete description. So there is a fundamental limit, and this limit is not on the way we perform measurement. The way we this limit is not imposed to, like, how we are taking the measurement, but it is a fundamental law of nature that we are prohibited of knowing mutually exclusive properties, or properties that makes the complete description of a quantum object. And this is what the uncertainty principle is, and this is why someone wise has said that we now know that we will never know. What we will never know is the complete description of a quantum object. The other thing that is visible from uncertainty principle is uh, that, like, when we look at the measurement of a spin along z-axis, we see, like, now we can uh, get either a plus or minus state, or we can either get a plus I or minus I state with equal probability. When we convert this probability of a state to wave nature, or to waves, then we see we can mathematically write it. And I'm not sure if you are able to see the formula down below, but when we mathematically formulate it, it tells us the principle of superposition. So it tells that if you are taking a measurement along the z-axis, and if result is maybe either 0 or 1, now you have equal probability of getting plus 1 or minus 1 along y-axis, or plus 1 or minus 1 along x-axis. So this is what the principle of superposition is. This is how we mathematically form or write the superposition. So at the end, like, we can define the quantum computing based on the knowledge we have gathered until now, that the quantum computing is a device that take benefit of superposition, and the quantum programs that we write for this devices, it take advantage of interference. It also take advantage of entanglement, but it for our purpose here, it takes you know advantage of phases. And the programs we write, in those programs we try to cancel out phases of to cancel out the waves of probabilities of undesired outcome. And we would like to get a constructive interference for waves which are associated with our desired state or the desired solution. So there are many applications of quantum computing, as I mentioned, like security, cyber security is one of them. And there are application in almost every field of science and mechanical engineering, or even in like finance. You can use quantum computers to get a optimized portfolio, or you can actually calculate the optimized return. So the possibilities are limitless. Yeah, I wanted to quote. I'm sorry, I don't remember the name of physicist, but he said, like, you know uh, the quantum computing, the power of quantum computing is equivalent to the power of electricity. So before electricity, like, everything was run on steam, right? So electricity change the things, like the way things were mechanically performed. So similarly, like quantum computing is going to leave an impact on almost all the fields of it's not only science, but almost all the fields that we deal with in our daily life. And we are at the very beginning. We are at the initial phase. And you probably have seen this picture and many presentations related with quantum computing. But this is how the classical computer looked like in 1950s, and this is how like our quantum computer looks like. So it looks even better. We are still in the same era of development, but yeah, hopefully we'll make a lot of progress in coming year with the launch of you know IBM's 1000 qubit computers. Things may change and it may never look back. So that's all I have, and I'm ready for any questions if there are any.
Participants, if you have any questions, you can ask in the chat box.
Jayesh, how could we motivate younger people to start working on quantum actually? What will you do?
Well, and this is why I mentioned about this videos people post, like the hype and all that. So it actually, when you look at those videos, you think like quantum computing is not going to come. And I have had like discussions with people um, who says like no, it is not going to happen, we won't be able to exploit that because there's a limitation by nature and all that. And uh, we'll have to look at the history and the way the classical computers have made impact. So initially it was thought that it is going to be difficult because people were working with like walls, and after the transistor was invented, everything has progressed. So it is actually uh, maybe just one invention in engineering, or one discovery may change the things, and it give it a pace that is required. And this is why I said like the applications are not limited to one field. So no matter like whether if you are a chemical engineer, or you are a biology student, there will be an application of quantum computing, or whether you are you are studying finance. So this is a good motivation, right? And the way things have progressed after 2016, um, it is just a matter of realization of hardware. You have algorithms, you have software in place, you have coders, like the people who can code, and analyst in place. So entire ecosystem is there. What we are waiting for is an hardware. And it's not only IBM which is working on hardware, but there are many companies. And if we read about, like people are trying to come up with innovative ideas, like using photonic computers. So using like photons inside a chip. So they are mixing the semiconductor with light. And some companies do not like disclose their progress. So I think this is the right time to enter in this space, if you would like to become a leader for anyone, for people and for organization. uh, and I have been following this space from long time, like you, Dr. Gandhi. So I did conduct the first training in my organization in year 2012. So people, they used to laugh at me actually. But they said like it's not going to happen. uh, so there uh, I am optimistic, and we are going to see this change in coming years.
Yeah, Jayesh, even I had the same experience when I
Right.
started.
Yeah.
They suggested me drop this field and start working on some other field actually. So, but
Right.
anyways, Sharon, we have some questions more. You can
Yes,
read.
yes. So there is a question from Srikant.
Mhm.
He asked the relationship between quantum computer and cyber security, sir.
Okay, so you know what? Uh, when we talk about the security over internet, so we use a protocol named as RSA. Like so, that's based on a mathematical framework. Uh, so if you can break that protocol, then your all your financial transactions, or the documents, the confidential documents, or things happening in a war place, uh, if you can just break the RSA algorithm in a time bound manner, that will become public, right? And that is, nobody wants that, right? So you need not RSA, but something that can take any type of cyber attack, that can not only immune, but that can also tell you that like there has been a software attack, so you will become proactive also. So that is where like quantum computing helps. And in our country, DRDO, and also now there was a conference few days back in Mahu, MHOW, where things were discussed around like implementing this QKD, the quantum key distribution for the military application, because any new technology is first adopted by military. So that is a rule, unwritten rule. So this is how these two are related. The quantum computing has potential to break the existing security. And if you it also provides you a solution. If you use like quantum key distribution, nobody would be able to break it. And also if somebody will try to break it, like you would get an idea. So this is how it is related with the cyber security. I hope I
Thank you, sir.
answered. Yeah.
Yes, thank you, sir. And we have one more question from Siddharth. He asked that how would an electron look like? Suppose we manage to take a photograph of it, and would we be able to understand its wave-like behavior by looking at it?
Yeah, I mean, this is why like this type of questions are not allowed in quantum mechanics. you know. So electron is a wave, right? And nobody has seen the electron. What you see actually is a probability cloud, uh, and that is also mathematically calculated. So how it will look like, or whether there is an electron, or whether there is an ocean of uh, you know what we call the field of electron. So in whatever we have learned in our school or colleges, it may be lie, right? Because maybe things are different. But maybe the way now this quantum field theory, or like the quantum electrodynamics, the way it describes the nature is very different from what we have learned. But what we have learned is experimentally verified. Not exactly that there is an electron, but we know, we have experimentally verified that there is an effect of electron. There is an effect of something that has charge 9.1 into 10 to the power sorry the mass of 9.1 and 10 to the power minus 31 kg, and charge of 1.6 and something like 10 to the power minus 19 coulomb. So that thing is there, but we do not know if that thing is a particle, or it is just a manifestation of some vibration and uniform electron field. Now, but the QFT physicist says that there is a uniform field associated with each particle, like electron, like quarks. And when we said like we have felt, and I'm not saying we have seen, we have felt an electron, it is just a manifestation of the vibration on this like uniform field that is there. So this is why like I mean, I'll give you a very simple example. 2 and minus 2 is 0, right? But in mathematics, I can create two objects out of nothing, plus 2 and minus 2. 0 is nothing, plus 2 and minus 2. So this is what the mathematics is, and it creates things out of nothing. It does not make sense, right? But mathematically it is possible, right? You can create two entities, plus 2 and minus 2. And this is how universe works. It works on the mathematics, and that has been proven again and again. If you look at like the relativity, the space is getting curved, the time dilations, these are all counterintuitive things in electrons at like multiple place, or entanglement. This is all mathematics. As long as mathematics says that it is possible, things happens. Now I'm not saying that, like, maybe there is a simulation, we are living in a simulation, and that simulation is using some mathematical equations. So I'm not saying that, but maybe that is what is happening. There is a possibility. So in short, yeah, and when you say like how it looks like, this question, um, is not correct.
Thank you, sir. So we have one more question from Akwel. How is quantum computers linked with business students?
Oh yeah, that's a very good question. Like, as I said, and I remember something a talk when they said term quant. So quant, if you are in business or finance, quant is what, measurement, right? This is a basic term in finance, and what you try to do is like you try to quantify things. Like you try to quantify, if I'm going to buy this asset, what would be the value of this asset in future. So how you look at it, you look at it based on, like, the past experience, the past values of that asset. Maybe it is a property or land, or maybe equity, liquid assets. Then the one way is to look at is like, the artificial intelligence you apply, which this world is driven by random events. Nobody had thought about COVID, right? Nobody had thought about the disruptions that we are seeing in today's world. So you can make, like, using maybe Monte Carlo simulation, or something else based on, and this is one of the project I suggested, like, to someone, that right now, this simulation that we do based on the random numbers, let's try to get the real random numbers out of quantum computer, right? Because that is only the real numbers. Otherwise, no, no, we do not have the real random numbers. Using We cannot get it using Python or classical computation. So one thing is, like, in finance, when you would like to understand what would be the value of your asset, or what would be the value of your portfolio, given random things will happen, given, like, the past data, given the fluctuations in market, what is the best possible portfolio you can get to maximize your profit. Or there are cycles in finance, like when you trade, uh, let's say, one currency to other. So there are, mathematically it is possible. Every time you convert your currency, you lose money because you pay commission. So if you convert dollar to rupees or rupees to pounds, but there are reverse cycles possible in mathematics, and finding those reverse cycle is an NP hard problem. It is a mathematics again. It's a mathematical problem. Using quantum computers, if you could solve that problem, you can do the reverse cycle. It does not mean that you again go back to the same money, but there is a theory, and there's a proof to that theory, that you can in fact do the reverse cycle and make money out of it. But these problems are NP hard. If you try to solve this using classical computers, it's going to take years. So these are like, one of many application. Otherwise, like, you can, if you are doing a business of like shipping, you can find the best route where you have to spend, the fuel is very costly nowadays, so you have to spend very less on fuel, and still you would be able to cover all the shipping addresses. So these are all optimization: how much you should buy, how much you can keep in your warehouse, what to do with the items. These are all mathematical problems. These are all optimization problems, and quantum computers can find the best solution that a classical computer cannot find in a reasonable time.
Thank you, sir. So I guess that's all with the question and answers. So thank you so much, sir, for imparting your knowledge with us and sharing your experiences and
Yeah,
enlightening
sure.
us. Thank you so much, sir.
Thank you very
Now,
much.
Yeah, Jayesh, thanks a lot. On behalf of our management, we would like to thank you for giving such a wonderful session. Thank you once again, Jayesh.
Okay, thank you for having me here. Bye bye now.
Yeah, bye. We thank all the participants.
participants, yes, participants, if you have any doubts regarding this session or the upcoming sessions, please do mail us. The mail will be available on Discord as well as on Hype. Um, so after leaving this meet, you will receive a feedback form through mail, and it's also shared in the chat box. We would really appreciate it if you would fill that up so that the insights would be better for us for improving the next sessions. The next session will be conducted tomorrow at 10 a.m. It's about quantum safe cryptography by Miss Gucha Malik, ma'am. So that's all, guys. The link for today's this session, the recording will be shared in the Discord. If in case you missed any part of it, you can just access that. So that's it, guys. Thank you for connecting with us, and have a great day ahead.